Hello! In this workshop we are going to simulate explosive welding. Here you see the dimensions of the explosive material, titanium part and steel part. Both titanium and steel parts are concentric cylinders. The inner cylinder is the titanium part and it is going to be welded to the steel part. We will use the axisymmetric model because both the geometry and loading conditions of the model are symmetrical. Note that because the explosive material is TNT, we need to specify dimensions for this part. Also, we must define an explosive point to start a simulation from there. Okay, the mechanical properties, boundary conditions and loading conditions will be presented here. Moreover, the simulation of the model in the software with necessary details will be explained. Now let's attend to the current slide. The TNT material is determined by the gray color, the steel by the green color, and the titanium by the red color. You can see the dimensions of all parts here. The explosive point is determined precisely in the middle of the TNT. Let's see the mechanical properties of the steel part first. Poisson's ratio, conductivity, elastic module, Johnson-Cook plasticity, expansion coefficient, specific heat, density, and inelastic heat fraction. Johnson-Cook plasticity parameters are specified in this table. Now let's see the mechanical properties of the TNT. To define the TNT, we will use the JWL equation of state. In this equation, we have conductivity, specific heat, and density. This equation will calculate the pressure caused by the explosion. Finally, the mechanical properties of titanium are Poisson's ratio, conductivity, elastic module, Johnson-Cook plasticity, expansion coefficient, specific heat, density, and inelastic heat fraction. Now let's start the simulation in the software. First, we must create the parts. As we mentioned in the slides, we are going to create all three parts as the axisymmetric type. Click the Create Part tool and from the pop-up window select Axisymmetric, Deformable and Shell. These settings are applied for all parts. Here we have created all three parts. For example, let's see the steel part. You can see the dimensions of the part and the distance between the part and the symmetric axis. After creating the parts, we must define the material properties. In the property module, we must define the material properties of each part separately. After that, we must assign the sections to the parts, which we have done it already here. In the assembly module, we must insert all three parts and place them in a proper position to assemble the model. Next, we need to create a step in the step module. The step must be temperature displacement because we want to simulate the welding and there is heat transfer, especially in the explosion welding. Also, we must use the explicit solver because there are non-linearity and large deformation. Therefore, the step will be dynamic, temp dis, explicit. The time period equals 1, 10 to minus 5 and the nonlinear geometry is on and the other settings in this window remained by default. We will use the pre-selected field output variables and set the number of the intervals 200. From the introduction, we said the ALE theory will be used for explosive welding. Now we must mesh the parts in the mesh module. The titanium and the steel need to have more mesh because they will be welded together and there be more accurate results. So the mesh size of these two parts is 0.0001. The TNT doesn't need a lot of mesh. Therefore, we used the local seeds tool and specified 10 elements for the width of the part. Next, we must assign the element type. So click on the Assign Element Type tool. Now let's go to the Job module. To refresh your memory, we created 3 models. One without the ALE named, Model 1, no ALE, the other 2 with the ALE, but different frequencies. Therefore, we created a job for each model and submitted. The model analysis without the ALE was aborted because of excessively distorted elements. Let's see its results. As you see, the elements have been distorted and it causes the job to abort. We can conclude that we must use the ALE, otherwise there will be errors in the analysis. Now let's compare the 2 other model results with different frequencies. The model 1 frequency is 1 and the job 3 is 5. Create another viewport through the viewport menu, align the 2 viewports vertically, then in one of them show the job 3 results, and in another model 1 results. If you look closely at this region in both models, deformation quality is better in the model with higher frequency, in job 3. Therefore, we have better deformation quality with a higher frequency but more process time. Now let's see the temperature results. The temperature is increased up to 1716 degrees centigrade. Also, you can observe the stress and strain results. Select the ODB display options from the View menu, select the Sweep Extrude tab, and sweep the elements to see the whole model. Here we only sweep 3/4 of the model to observe the results better. Moreover, you can apply the Free Edges option to see the model like this. Click on the Animate tool to see the animation of the whole process.